Hello, everyone. I'm Serge Rodney. I'm pleased uh, to present you our work on BioLockerA. So let me share my slides. Uh, okay, so that's BioLockerA. It's a authentication mechanism which is based on Fingervein Biometric. It's a joint work with Betül Durac and Loïs Huguenin-Dumitan. So what we want to do is that we want to take some access control system which allows people to log in on desktops by means of logging a password and to enrich this system by using biometry. And our goal is not to add too much on the existing system. So we take the existing system, and what we do is that we add a piece of software on a desktop, we add a server, we add some biometric sensors, and we don't want to add too much on a desktop. So we will have some biometric capture by the sensor, and it will communicate to a server, which will do the biometric verification. We want also to have privacy protection for the biometry, and we want the system to be based on finger vein recognition. So finger vein is something which is presumably more secure than fingerprint, because fingerprint, you let your fingers everywhere on everything you touch. But for finger vein, it's hard to steal. So let's talk first about finger vein biometry. So how does it work with our sensor? So we have a sensor where we insert a finger. So you have a picture here. We insert a finger. So there is a rack of LEDs which gives some infrared light. And the infrared light is captured by a camera which is below the finger. So that's the side view. And on the front view, you can see the finger here, the rack of LED here. And you can see that there are actually 3 cameras which take pictures of the finger vein through 3 different angles. And we call it a 3D finger vein recognition. So we use 3 cameras. We have a Raspberry Pi which controls the cameras, the communication, the crypto part, etc. The finger vein is harder to steal than fingerprint, as I mentioned. And the usage of the 3 cameras makes it harder to corrupt by spoofing attack. When we take a picture, so this is a picture which is taken by the front camera. So it's a picture of a finger, and you have also some reflection from the side. So first thing we have to do is to clean up the picture. Then we rotate the finger, and then we apply some extraction algorithm, which is a Miura et al. Algorithm with Limask, to extract a black and white image which represent the finger veins. So once we have 2 black and white images, we have a matching algorithm to try to compare the 2 finger vein patterns. And how does it work with the Miura et al. Matching algorithm? We try all the possible translation of one image on the top of the other. And what we do is that we do the intersection. So we look at the white pixels which are in common. We count how many white pixels are in common, and we divide by the number of white pixels of the first image and the number of white pixels in the second image. And we take it as a score, and we take the maximum over all the translation. So the score is a maximum of overall translation of this ratio. So the score will always be between 0 and 1/2. Once we have one score to compare 2 images, so we need to figure out what to do with 3 cameras and maybe with several captures of images. So for this, we have to develop the biometric recognition algorithm. This is actually a hypothesis testing problem. So the idea is that we take some images of fingers. So either we'll have pairs of images coming from the same finger or pairs of images coming from different fingers. And when we compute the score, it will follow some distribution, and we have to decide if it comes from one distribution or another. So the problem is that we have as input a sequence of scores. So those scores are maybe different from different cameras and maybe from different captures. And we have to output a result. So the result will be either accept, reject, or undecided if it's not feasible to take any good decision. If it is undecided, it means that we need to take more images and to collect more scores to be able to take a decision. So that's the principle of the sequential distinguisher. So how our algorithm works, so we compute the likelihood ratio, which is the probability to observe the scores that we are given if we follow the same finger distribution over the probability to make the same observation if we follow the different finger distribution. So we compute this ratio. If this ratio is larger than a threshold, we accept. If it is lower than another threshold, we reject. And in between, it's undecided. So the theory which is behind allows us to define these two thresholds based on some target false acceptance rate and a target false rejection rate. And at the end, we obtain a false acceptance rate and a false rejection rate, which are a good approximation of the values that we have given as input. Of course, if we are too greedy with a false acceptance rate and a false rejection rate, the consequence is that most of the time the answer will be undecided, and we will need many captures to be able to take a decision. If we're not too greedy, with one or two captures, we are able to make a decision. So the formula, if we compute the logarithmic likelihood ratio, it becomes a sum. So for this, we need to assume that all those scores are independent with the same, or with they are independent. So this product, this ratio becomes a product of ratios, and as a logarithm, it becomes a sum. So the sum will involve the average score with respect to the two distributions and the standard deviations. So you can see here a plot of what we observe for the distribution of a score if we take different fingers, and the score when we take the same finger. So from this curve, we can see that we can make a distinguisher, and it works. So we implemented it, and we obtained some good results actually with one or two captures. So here is the algorithm more precisely. So we are given a list of scores, or a list of triplet of scores, because we have 3 cameras. And we accumulate in some accumulator delta LPDF given by the score on the camera. So it will compute the sum that we have here. And after that, based on this accumulator value, we decide to accept, to reject, or the undecided result. So that's a decision algorithm. We also have an algorithm to define what is a reference template when we enroll someone. So when we enroll someone, we'll take several pictures of his finger, and essentially we'll take the best one following this type of algorithm. So I won't enter into the details. And after that, we have to talk about which cryptographic protocols we implemented to secure all this. So remember that we have a system with users. So users have fingers, they know a login and a password. We'll have biometric sensors. So those sensors, they are associated to a serial number, and they have also a key pair. So those keys are used essentially to sign. So this is a signing key, secret signing key, and this is a verifying key. For the enrollment station, to enroll someone, we have a similar triplet. We also have the password directory, which is database of login and password, which we enrich with a pseudonym for for the privacy of people when we store the biometry. We have desktops, and we have the server doing the biometric matching. We want the server to be completely stateless. It doesn't need to remember a state. So we send a query and he answers, and he doesn't have to remember that we queried it. The server will have two databases. So one database of serial numbers, either for the sensor or the enrollment station, and their public key, and a database of a pseudonym of users, their finger, so which finger is taken, and the reference template for this finger. They have also a key pair, so it is a pair which is used to encrypt and to decrypt, a public key to encrypt to the server and a secret key for the server to decrypt. And there is also a long-term symmetric key for the server to encrypt messages for himself. So that's how we deal with the stateless part. So when we have to remember, when the server needs to remember one thing from one query to the other, the idea is that he encrypts what he has to remember and he sends it back together with the answer. And next time when we query it, we have to remind the server about this, so that he's able to decrypt what he encrypted for himself. We assume that the public key of the server is distributed to all participants. So how is the system working? So first, a user would type his login and password on a desktop. So desktop will verify it on a directory so that the system which is already implemented, on which we add our new system, biometric system. So for this, on a desktop, we need to add the software for the next protocol. And we also need to add a pseudonym in this directory. So the pseudonym for every user. So first thing to do is that the desktop will query the server, say, hey, so I'm this desktop and I want to authenticate this user and I will use this sensor. So he has to give this information. At the same time, it gives a key, which is used to encrypt the answer. And the answer will actually encrypt a token. So that's what he has to remember for himself. With this token, the desktop can go to the sensor and say, here is a token from the server. The sensor will capture the biometry of the user and respond. And the desktop will be able to forward to the server. It will be compared with the reference template, and the answer will come back to the desktop. And depending on the answer, either he will accept the user, reject it, or ask for a new picture of the image of the finger. For the enrollment, is very similar. I won't enter into the details. And eventually, if all the primitives that we are using are secure, we can prove some security. So actually the difficulty to prove the security is essentially to prove that every participant is seeing the same information for the same transaction. So we have the security for the enrollment, which says that if the enroller believes that some person was enrolled with a given biometric scanner, then it must be the case. And if the server enrolls someone, it's because enroller asked for it. There is also security for access control. If the desktop granted access to someone by using a biometric sensor, then it must be the case that it was validated by the server somehow. And there is also the privacy for the biometry. So far, the privacy is protected only with the pseudo. So we connect the user to a biometry by using a pseudonym. Of course, the biometric information stays local on the server, so it's captured by the sensor and it's sent securely to the server, and it only stays on the server side. So that's what we did. And as a future work, we'll have to study how the finger vein behave on a long term. We'll have also to strengthen the privacy. So far, all the biometric information are concentrated on a server, but to have it more privacy preserving, we would probably have to distribute the server or to do some more complicated privacy preserving operations. And we'll have to deploy it. And for that, we were happy to work with the company Global ID, which is trying to deploy this system and to build those sensors. So that's it for our work. So thank you very much for your attention. And with this, I'm happy to take question if any. Thank you very much.